Great. So this is, I guess, number 4 in our series of uh, deep sky imaging acquisition, focusing on what we can do to set up our instruments so that we can get great subframes to make a really nice image. So this portion is regarding the electronics, and just want to, this is kind of a theme that I touched on at the beginning, which is with astrophotography, really how far you go into any of these subjects depends on how much you want to do, how deep you want to do your integrations. If you want to do, like a half a dozen targets a night, that's cool. If you want to do one target over a couple of weeks, that's also cool. It just depends on how far you want to push each of those, and a lot of the points we've made in the previous sessions and in this session kind of go to varying levels of how far you want to push the hobby, and how deep you want to go in your images. So yeah, last time we've gone through 3 of these already. This is the 4th one, as I said. We've had mechanics of setting up your rig. That sort of sets up the fundamentals of making sure your mount is stable and your tripod stable, and getting best practices in for that. And then the optical considerations of your telescope, and things you have to consider for filters and correcting aberrations in your telescope with field flatteners or focal reducers. And then last time Jeff introduced guiding and why we guide, the purpose of it, all the options and settings, of which there are a lot. But he went through that portion of astrophotography. And it was a really great overview of guiding. And this time we're going through the electronics portion. This will be centered mainly on the sensor, and just discussing how the sensor transforms the light that we collect through our telescopes into some sort of signal that we can measure and turn into an image. So to get started, we'll start with imaging sensors. And the fundamental effect of why we can turn light into an image, a digital image, comes from the photoelectric effect, where light comes in and strikes an atom that's loosely binding the electrons, and it kicks it up to a free state. So those electrons can now collect. And this has been known since around the 1800s, and was kind of perplexing as to why that happened. Albert Einstein came along, and in 1905 he proposed an explanation for this called the photoelectric effect, and was awarded the Nobel Prize in 1921. And this effect ranges from our sensors that we use in digital astrophotography, but also has a big influence in the solar industry as well. So it's the basic principle behind all solar cells that transform light into electrical energy. But in our case, we're not getting electrical energy, we're actually getting an electrical signal from that photon signal, from the light signal. In a sensor, there are pixels, and there are numerous pixels, millions of pixels in today's modern sensors. And each pixel is a fundamental unit of the camera. It's a photoactive unit that when a particle of light called a photon strikes this unit, it kicks up those electrons, and the circuitry in the camera can read those electrons from each individual pixel. There are various ways that that reading is done, and that kind of ties back into the 2 main different types of sensors that are out there. But long story short is sort of a bird's eye view of this is that the light goes in, hits a pixel, converts it to an electron, and then that electron gets read by the circuitry of the camera. So pixels are kind of carbon copies of each other across the entire sensor. The pixel usually is a square pixel. In some cases, they're rectangular. But basic properties are that each pixel has a certain width and height, It also has a pixel pitch, which is the spacing between neighboring pixels. And more often, the pixel width and pixel pitch are very similar, very close to identical. In some cases, you can have spacing that the pitch is different than the width, so that your pixel scale calculations might be a little bit different than what you would assume, assuming that the pixel width is the same as the pitch. But in either case, you can compute the image scale of your camera on your telescope using this simple formula. In the back of my head, I always just do 200 instead of 206 so that I get a rough approximation whenever I'm doing these things without a calculator or anything. But pixel size times 206 divided by focal length. The reason I do 200, say, for example, I have a 5 micron pixel. 200 times 5 microns is 1,000. So I know that at 1,000 focal length, I'll have 1 arc second per pixel. At 500 millimeter focal length, I'll have 2 arc seconds per pixel. So that kind of simpler reduction allows you to, get a quick estimate of what different sensors, how they look, how they perform on different telescopes and different focal lengths.
Gabe, just one quick question. Yeah. The way you've got that shown, the pixel pitch is the distance between the center of the pixels?
Yeah.
Okay, because you said it was the space between pixels.
Right. I may have misspoke there. The space, if the space between pixels is 0, then the pixel pitch is the same as the width. If it's non-zero, okay, then you'll have some pixel pitch is larger than the width. Yeah.
Yeah. Okay.
I think so. All right. So I want to kind of do a deep dive into just one pixel and what it does. And this extends to all pixels in the sensor. I'm pulling from this link down below, which if you're interested in this kind of stuff, I encourage you to go through their blog. They have it's a 4-part blog talking about the pixels and the effects of light accumulating in those pixels and what type of other effects you can have. I'm going to do kind of the Cliff's Notes version of that real quick, but there's a lot of really good detail in that blog. So at high level, just one pixel is, you can just imagine, as a bucket. And it's a bucket that collects photons, much like a bucket that would collect rain. And the bucket is kind of reflects how bright that piece of the sky is. As if the photon flux, which is the number of photons crossing your pixels per second, if the photon flux is high in a given amount of time, you'll have your bucket or your pixel filling up faster. If it's low, if it's a dimmer object, your bucket will fill up a lot slower. And this, the height of how high you fill that pixel with your photons is how bright that pixel will be. So this saturation level of the bucket is directly related to how bright your subframe pixel will be. Okay. And so if you compare different cameras, they'll have this thing called full well depth, which is how many electrons this bucket can hold. In the case of this camera from ASI, the full well depth is a little over 51,000 electrons. In the case of this KAF 8300 Kodak sensor, the full well depth is a little over 25,000 electrons. So you can see that if you have a given number of electrons, you can fill the shorter bucket faster than you can with the smaller, the larger bucket. And conversely, you can image for a longer amount of time with the tall bucket compared to the small bucket, or otherwise you get into saturation issues. So this capacity is related to the electrons that get converted from photons, and just tells you how deep your bucket is. It's a direct comparison to how deep that bucket will be. So if you just keep collecting photons, eventually you're going to run into an issue where you have too many photons converted into electrons, and those electrons will spill over. And that's what happens when you saturate your chip. You can saturate your chip by maybe setting the sub-exposure length a bit too deep, a bit too long, and stars will saturate, or the core of bright galaxies or nebulae will saturate. And in this case, if you have a bucket that is, in this case, 100 electron capacity, you put in 75, you get 3/4 filling. But in the half-size bucket, you'll have a 25 electron spillover. And that doesn't add extra information because you're already saturated. You can't store any more information in that bucket. So in a sense, we should try to never have that happen, because you're losing information in your images, and when you try to combine them, you'll have issues. For example, if you oversaturate stars, then oftentimes you'll have issues with getting the color of those stars coming through, because all the stars will have lost their RGB ratios. They'll all be at maximum. So if you have some really blue stars, the blue stars will hit the photons from the blue filters will hit that capacity first. That'll saturate, and then the red and green will saturate later. But if they all saturate together, then you're going to lose all that blue color from your stars. So it's good to keep an eye on the saturation of your stars, and also of bright objects like galaxy, nebulae, and so on. In the post-processing, you can try to retain the color saturation by looking at the sort of halo around the star, because that tends to reflect, or tends to be similar to the color of the star.
Hey, Gabe,
you will also, yeah, go ahead.
Sorry, you said you should look at the saturation of your stars. How do you do that while you're imaging?
Yeah, so so it depends on what type of acquisition software you use. Sometimes in some acquisition software, you can inspect the image on a pixel level. What I would do is, typically for me, I would take an image and then inspect it. What I usually do is inspect it in PixInsight and check the ADU value, or if it's on the ratio of 0 to 1, I check to make sure it's not close to like 0.9 or anything like that. And then I bump back the exposure, and then once I'm happy with that exposure, then I make a note that that's sort of the exposure that I want to aim for in most of my subs. So if I do get a lot of really high, if I do saturate my stars, oftentimes when you take off the stretch, if you're looking at it in a linear fashion, you'll just see white circles, and those white circles are also hints that you're actually saturating those stars, instead of seeing a nice sort of rounded star profile. Does that answer your question? Okay, cool. Yeah, and also another tricky thing with stars are blowing out cores of galaxies and nebulae, that in post-processing, a lot of times we try to use HDR methods and things like that, and those have a difficult time working on areas that are oversaturated. So that's another point to make on trying to not get to a saturation level. So yeah, this is just a comment about, like, you have only so much space to put electrons into your bucket, and if you go too far, you'll overfill it. The other portion for cameras is that the amount, or the rate at which one photon is converted into an electron differs by camera, for a variety of reasons. It could be the pixel material itself, or it could be what's in front of the pixel. Maybe there's like a cover glass or something like that that can reduce your efficiency. But in the end, there's a transmission efficiency, which here it's more or less like a quantum efficiency of the chip, that for a given photon, 91% of the time, in this case, in this ASI 6200 case, 91% of the time it'll get converted into an electron. And over the spectrum, it's not 91. I think this is a peak quantum efficiency. But broadly, this is a good number to track when you're comparing cameras, just that peak quantum efficiency. Rarely do camera suppliers give like the full absolute quantum efficiency. Usually it's either a relative quantum efficiency or a absolute quantum efficiency at peak. But this is also a value you want to compare against different cameras to see which ones might be good to choose. So this is an example of what happens to those photons as they come in to your bucket. If you have 100 photons in, and this is a 100 photon size bucket, and your quantum efficiency is 85%, you'll get around 85 electrons out of those 100 photons. But if you have a smaller quantum efficiency, you'll have a smaller number of electrons captured, and that just reduces your overall signal. So you have to image for longer with the lower quantum efficiency in order to get the same amount of signal. And this quantum efficiency is just a product of the chip. There's nothing you can do with the settings in ASCOM or anything like that to change this. It's just, it was basically set at the manufacturer when they manufactured the chip. Okay, so gain and ISO, that's also another thing to consider with cameras and electronics. Basically, gain is, you might think of gain as just a way to image faster, get better signal faster. But really what it does is it doesn't change how fast this bucket fills up. You're still getting the same amount of photons. That's dictated by the pixel size, the focal ratio of your telescope, and how bright the object is. And maybe if you have some aerosols or something like that in the atmosphere. This stuff is irrelevant to what type of settings you make in your in ASCOM or in your camera driver. But gain or ISO, this effectively changes how tall or how deep that bucket is. In a sense, what it's saying is that for every photon that goes in, multiply that photon by 5, say, and that gets converted into maybe 4 electrons, whereas before it would be roughly 1 electron. So you're piling up more electrons, but you're only getting that based off of 1 photon. So the counting isn't like you're actually getting 4 photons, you're still just getting 1. And the way that sampling is that you're just boosting the signal artificially and not increasing your dynamic range or anything like that. So in the kind of bucket view, these blue lines are to distinguish the fact that electrons can only sit here, here, here. You can only have 1 electron or 2 electrons or 3 electrons or 5. You can't have half an electron. It's part of that sort of fundamental unit of charge, which is the electron. You can't have anything lower than 1 electron. So what happens when you go from a normal size bucket to your high gain or ISO bucket is you're effectively shortening the size of that bucket. You're going to fill that bucket up a lot faster. This is different than the full well picture. We're actually taking this lower portion and expanding it into this portion here. And so there are trade-offs to changing the gain or ISO. The pros are that your bucket fills faster if you want to do faster imaging. But the trade-off of that is that you do have a lower dynamic range. So really, in the end, you're not getting a higher signal-to-noise ratio or anything like that by increasing gain or ISO. And just for concreteness, the gain is defined as the number of electrons per ADU. And this is the digital unit that you read when your image downloads. Yeah, here it is. It's the digital unit that you read off of your image. And what's going on here is that there's an analog to digital converter, which takes the electron signal, which is an analog signal, and converts it into a number, a discrete number. And each of those electrons get converted into a number. And depending on what type of ADC you have, it converts it up into these different levels. So for example, if I am on a 12-bit camera, I only have around 4,000 levels that I can put electrons into. If I have a 16-bit camera, it's up to 65,000 levels. And what happens is that for your bucket, if you have high gain, you're effectively stretching those levels into to really fill out the capacity of this bucket. So whereas before with low gain, you would fill out maybe a quarter, with high gain, you would fill out the entire bucket in that amount of time. But we're not changing the number of levels. We are projecting, say, if I fill out to level 100 in low gain, I would fill out to level 400 in high gain. So I'm reaching that saturation point in my bucket faster by multiplying the signal. But in no way increases your signal to noise or anything like that. You have questions here? Okay. So there are other things that can be done on the hardware side. Different cameras have these, other cameras may not. One is the micro lens array, and what it is just a little tiny lens in front of the pixel.
Excuse me, Gabe,
yes.
can you back up just a second?
Sure.
Yeah, I was having a hard time finding the mute button. Okay, so my understanding of gain is you've, and I have a picture of this, is you've got so many electrons in your well, and what you're doing is assigning a numerical value to that number of electrons based on your A to D converter, right? So for the same for the same number of electrons in your well, by adjusting your gain, you're just getting a different A to D value, right? You're not changing anything relative to the well.
That's correct. Yeah.
And so the gain is just used to maximize the range of your A to D converter. Then is that and not it's not actually doing, like you said, nothing to the well itself.
Yeah, it's not. Yeah, the well depth and those things are all physical things that can be changed with your software or the gain settings. And like you said, the gain setting will translate how full the well is into this 16-bit number or 12-bit number.
Right. Okay.
Into that ADU number. And if it multiplies it by 1, say it's a 1-for-1, the gain is 1, then what it will do is for, say, 10 electrons, it'll get 10 ADU. But if the gain is 4 times that, then for 10 electrons, you will get 40 ADU. But they will move in increments of 4 instead of increments of 1. And that's why noise often scales along with the gain. So in the end, you're not changing SNR. Yeah. Good question. Good comment.
Okay,
yeah.
Sorry, one more question about gain.
Mm-hmm.
Can you explain unity gain and what that means and why they tell you to image at unity gain?
Yeah, from what I understand, unity gain, I think it might be different depending, because I've seen unity gain be specified as a number of electrons per ADU that's different than 1 in some cases. But from what I understand, at least from the ASI camera that I have, unity gain is the highest dynamic range setting, so that you can you're not saturating the image faster. You're getting a better SNR overall with that setting. If you change your exposure times and so on to compensate for that, so that you don't fill up the bucket too fast, you don't saturate your image. So unity gain is the thing with the highest, from what I understand, is the thing with the highest dynamic range. And I'll go over dynamic range in a little bit, but in some cases, I would expect the unity gain would just be 1 electron per ADU. But that depends on the well, the dynamic range depends on the well depth and the read noise. So in some cases, 1 ADU is the unity gain. In other cases, it may not be.
But at unity gain, though, for a CMOS chip, that's your highest read noise, isn't it?
Yeah, that makes sense. Yeah.
So in our little equation that we looked at for the optimal subframe size, it was like 10 or some factor times the read noise squared over the light pollution.
Yeah, we'll get to that expression.
Yeah. Okay. All right. Yeah. So there's a trade-off there. So because I just bought my first CMOS camera, and basically it has this step function at a certain gain.
Yeah.
The read noise just boom drops way down.
Yeah, that's my understanding of it. Is it's where you get the highest signal to noise ratio. The camera. I know you guys talk about that, but for me, my simple mind, that's kind of how I think about it. Unity gain is that point where you get the maximum signal with the lowest amount of noise proportionately.
Yeah.
Okay.
Yeah, we'll get to a little bit more on that when I did talk about noise. Up till now, I've just kind of used the term noise, but in a little bit, we'll get to what that means. Some improvements for sensors, at least. What you can do is when you research sensors and look at what might be best for you, there are two kind of improvements on just a normal pixel, the notion of a pixel that I had earlier. One is to use a micro lens array, and oftentimes the photo sensitive area is this little blue slab here, and you'll have some circuitry or some filters that that block all of the light that's collected in this pixel, or this the width of this effective pixel, whereas the photo sensitive area is much smaller than that. But what the micro lens effectively does is it focuses that light so that it gets the rays that would not be absorbed by the photo transistor, and focuses it into the photo transistor, so that we can effectively collect a lot more light than we would be able to before. So this is a great addition to improving sensitivity of a sensor. Some drawbacks are depending on the sensor and depending on the cover glass in front of the CCD. You can have odd reflection artifacts. I think this is present in the ASI 1600, where if you image near a very bright star, you'll have these reflection artifacts where you can actually see the array of the micro lens, which is kind of neat, but gets annoying because you want to try and process that stuff out to get good looking bright stars. The other thing is that there are, depending on how it's designed, there are diffraction artifacts, and I think that's the case with 8300 Kodak sensor that I've had in the past, where you do have diffraction artifacts, sort of diffraction spikes along the up, down, and left, right direction, which coincides with the pixel shape. On very bright stars, they're noticeable. On dim stars, they're not too noticeable at all, really. So that's the micro lens array. It's been around for a while, but I think the more recent development is the backside illuminated sensors, where instead of all the circuitry being in front and it blocking the light that would come into the photo transistor, it actually flips the metal wiring and the this photosensitive substrate around, so that the metal wiring is behind the sensor, behind that the photosensitive area, and the light just gets collected there. And this increases the sensitivity of the camera by quite a lot. I've noticed on my camera that has this compared to older cameras. So those are some things to look out for if you're looking at cameras and thinking about either upgrading or getting a new camera. What types of improvements are out there? Okay. I want to go through two different types of sensors. One is the CCD, and one is the CMOS. The CCD is the earlier, more popular form of electronic imaging. The way it works is, if you look at this little cartoon over here, is that as photons strike from below and turn those into electrons, they collect into this well here, and by changing the voltage adjacent to that well and turning this voltage on, they can distribute, turn this one off, they move over here, collect, turn that on, they distribute, turn this off, they collect over here. So that way you're able to move the electrons from one part of the image all the way down to another part of the image by this cascading voltages across the array. And when you reach the end, you get to a readout point where these charges are incrementally read, so that you know that it came from each one of these sites, and that gets mapped into an image like this. So one thing about the CCD is that it has a global shutter. In many cases, you're going to need a shutter in front of it to block off the light. You can't have a dark without a shutter because it's just going to be sensitive to all the light that gets collected, that gets put into each pixel. Another thing is that because of the way that this is moving across the chip, if there's any defect in one of these pixels, then or any defect in the way that this chain is read, then you'll have what are called column defects, and that's shown here. In CCDs, older CCDs or CCDs with a little bit of damage in them, you'll have these column defects that are of varying brightness. And usually these aren't a problem. You can calibrate these out. You can have a setting in, say, PixInsight that has this cosmetic calibration to remove these column defects. In comparison to CMOS, which I'll talk about in a little bit, one big plus for the CCD is that you can bin to your heart's content without any read noise penalty. And the reason for that is read noise is a noise that's added during the readout process. And this is each of these sites collects the photons, and then they move down the chain, and the readout process is done at the very end. Whereas with a CMOS, the readout process is done at each pixel site. So you can't combine pixels in the CMOS, which I'll move to here. You can't combine pixels in the CMOS without adding the read noise together. So yeah, the CMOS, this is the way the CCD works. As these charges move down the chain, that's what these blue arrows mean. And then the charges read down the chain this way as well to the readout. So you can group these pixels together, and the readout still occurs over here. This is where the noise gets introduced. That's why in binning in the CCD, you don't get any read noise penalty. But in the CMOS, if you try to bin 2 by 2, you're going to have 1, 2, 3, 4 times the read noise in the binned image. So CMOS, you're going to have a read noise penalty with that binning. The other plus sides of CMOS, though, are that it's newer technology, and typically the read noise itself for one pixel is a lot lower than CCD. So that could offset some of those effects that I was talking about. There in some sensors, some CMOS sensors, the amp glow is quite strong and can cause calibration issues and things. I think with the newer sensors, these become less of an issue. The amp glow does. Another thing I'll say is that, which here at the top, is that because each pixel has a readout, if you're imaging a lot of short subframes, what's going to happen is, because each image has its own circuitry, each one of these little circuitry elements adds heat to your sensor. So it's going to be harder to cool effectively if you're doing that, if you're doing a lot of imaging at a very frequent pace. But if your subs are quite long, then it's pretty much a non-issue. All right, binning. So I talked about binning and how read noise affects that. Binning can increase the signal in a sense, but the trade-off is that the resolution is not as good. So we've been through this with the optics discussion about what your optimal pixel size should be, pixel scale, how many arc seconds per pixel should you image at, and depending on your local conditions. But Generally, as you go to higher binning, you're going to have more blocky stars, and it's just where that cutoff is where you should, you know, whether this looks too blocky or you want to get a star like this and then do some deconvolution on it, depending on your telescope and your pixel size and so on. And at that point, you need to consider CMOS versus CCD, how the binning affects the read noise for those two. Any questions about sensors before we move into noise? Okay. So noise is a big issue with astrophotography. We're imaging incredibly dim objects, and we get to the point where, you know, when we're trying to image like a dark nebula or something, noise is always a huge issue with, just because it's so incredibly dim. So there, in my view, there are two components to noise. One is the amplitude of the noise, how much additional signal does it add to your image, and the other one is what I am just saying is dispersion, which is the random part of that additional signal. So, for example, if I have an image that I take, and it has a dark noise component that adds, say for sake of argument, 100 electrons to each pixel. That's an incredibly noisy dark component. But the 100 that I'm adding is overall pixels, but it's actually 100 plus some fluctuation about that 100 value. And we can subtract out the 100 to return the sort of ADU or pixel. You know, if you have gain of 1 electron per ADU, we can return that down to what it was before we added the noise, but you can never subtract out the fluctuation. So if we go to this image, this static image, back before TVs became digital, we all saw these types of things on our TVs. And if you add this to your image and say that the gray portion of this is 100 electrons, and the brightest white is 130 electrons, the darkest dark is 70 electrons. You add this to your image, you can still subtract off 100. But what is still added here, that's spatially added, is that plus 30 minus 30. And that's what I'm saying is the noise that's the real problem that we can never remove from one sub. The way we remove that is by stacking to reduce that overall dispersion effect. So really the big problem with noise is the dispersion part, where we can have one pixel at a value and we have no control over what the next pixel value, the neighboring pixel value is. It could be plus 10, minus 10, anything along those lines. So really what I call noise here is just random fluctuations that can't be calibrated out. They can't be subtracted. They're added and then they're there. You have no way of removing them. And so if we look in our bucket, we have a lot of components that make up our image. We have the signal from our target of interest. We might have portions from light pollution. We have the read noise and then dark noise. And each one of these has this dispersion. We want to minimize as much as possible each of those dispersions, and the way we do that is through stacking and calibration. Dynamic range is really a statement of how much signal to noise you can get, or how much how clearly you can see an object's dark, like very brightest and very darkest areas clearly above the noise. So the way this is defined is we take the full well capacity, how deep the bucket is, and divide it by the read noise, and then do this calculation on it. We can do it in terms of decibels, and this would be the calculation for that. Or if you're into classical photography, do it in terms of stops, and this would be the calculation for that. You would use log base 2 for that. And this is a way to kind of gauge, like, how does this camera compare to this camera? If this camera has 85 decibels and this camera has 73 decibels, the 85 decibel camera will be able to image an object, image the bright areas of that object, as well as the dark areas of that object, without clipping the bright areas while maintaining the same level as the dark areas. So in fact, I did do this recently with a newer camera that has a very high dynamic range, and compared it with an older camera that had a very, well, I think it was that 83 decibel versus 69 or 70 decibel dynamic range difference. And I imaged Andromeda Galaxy. And as you know, Andromeda Galaxy has a very bright core, and it's really easy to blow out that core. With the newer camera, higher dynamic range, I was able to get the core not blown out and still get a lot of the really good detail in the arms and fainter extremities. So that's what the higher dynamic range will let you do. It'll let you image an object like M31, M42, and resolve the core, still get the faint stuff in the outside, and get a good image that way. Dennis, you had a question?
Yeah, I was just going to say, is read noise synonymous with the bias?
Yeah. The read noise is can be measured directly from the bias. Yeah.
But so, are the terms interchangeable when people talk about bias noise and read noise? Are they talking about the same noise?
I think in that context, bias noise is synonymous with read noise, like up to the point that you don't have any static, like maybe banding or anything like that in your camera.
Okay.
Banding that changes. If we're talking about just a fixed noise pattern, I think read noise characterizes what that noise dispersion looks like. And then there are other effects too, some sort of spatial noise like banding or something like that. And in that case, you can characterize that by looking at other properties of that bias, like the Fourier transform of it to look at how that spatial noise looks. But read noise is more just a number to say that the noise in this bias frame has this type of dispersion. But there are other effects in the bias that, if you say bias noise, could mean other things in addition to read noise, I would say.
Okay. Okay.
Yeah. And by the way, this expression is the best you can do, because really it's not just read noise that we consider noise that is a problem. This expression just tells you the maximum divided by how much noise you expect. So it's this ratio, and this, just by eye looking at this, it's probably a really bad, I mean, these bars are not to scale, but really bad dynamic range. I would say this is probably like 8-to-1 or something like that, the maximum to where the noise is. But this read noise is just read noise, when in reality you should be adding dark noise plus read noise, because this is the lower floor. This is your starting place. Say you take a 5-minute exposure. This is where the noise level is. So it shouldn't be just read noise. It should be read noise plus dark noise. But yeah,
so
go ahead.
Gabe, are you lumping in shot noise into the signal?
Shot noise is not in this calculation. This is more the dynamic range in this case for this expression is more just a statement of how much extra signal you can get into your bucket without saturating it. Shot noise is something different, and we'll get into that in a little bit. So the reason this expression is mainly written as full well capacity divided by read noise is that you do have a handle on what this component, the dark noise, looks like. So yeah, I guess I'm getting a bit too fast on this. So read noise is just the bias, effectively the bias, and you can calculate that. If you take 2 bias frames, subtract them, find the standard deviation of all the pixels from that subtraction and divide by square root of 2, then your read noise is just that value in ADU. If you multiply that by the gain, then you get the read noise in electrons. And and yeah, so this is the way you can calculate it. This is different camera to camera, and actually even the same sensor with different camera housings can have different read noise. The same sensor from different manufacturers can also have vastly different read noise, depending on the electronics that are put in to combine with that sensor. So this is our starting place down here, and it affects our dynamic range. The other component is thermal noise, which is the dark current. And because we live in a world that has, we're around 300 Kelvin, we're not near absolute zero. As you know, that as you decrease temperature, the electrons, the atoms begin to slow down. They have a lot lower movements. And the movement of electrons is a current. And in a sense, what the dark noise is just the thermal fluctuations of those electrons. I'm glossing over a lot of interesting science in there, but really this type of current is measured in our sensors and is temperature dependent. It's measured in the units of electrons per second. So if you image twice as long, you're going to get twice as much dark current. But you do have a handle on this, which you can decrease this dark current by decreasing the temperature. And this is a plot that I pulled that shows temperature versus dark current in electrons per second for a lot of different cameras, sensors, and so on. And you see generally, if you look at like one camera and the measurements, as you decrease the temperature, you decrease the amount of dark current in every case. Now, where you are depends on the sensor. So for example, at 0 degrees Celsius, depending on what sensor you have, you're going to have intrinsically different dark noise. But if you decrease by 10 degrees Celsius, you're going to, in all cases, you're going to decrease that dark noise level. Let's see. Yeah. So going back to this discussion, what should we put down here? Here it's read noise. It really should be read plus dark, but for the most part, it's just read noise because we have that handle on temperature. We can lower the temperature and make that dark noise much lower than the read noise. And that's what this is showing. So different dark noise at 25 Celsius, 0 Celsius, -20. So as you decrease the temperature, this is going lower. So if you want larger exposures, you should decrease the temperature more to offset that dark noise, to make sure that your only noise component is the read noise. And again, this read noise we can do nothing about. We just have to live with it because that's a product of the camera that we have. So overall best case is just cool your sensor as much as you can to reduce the dark noise and bury it underneath the read noise. And that's why, if we do that, that's why this relation is really sort of the best case dynamic range. Okay, so this is an example of the camera that I have. This shows the dark current in electrons per second in 1 pixel. And so I read off this, the values on here, and you can get a relation like this, which shows that you have this many electrons per second, and you plug in the temperature of your sensor here. And what this tells you is that at 0, if temperature is 0 Celsius, this is 2 to the 0, so this is 1. So this is the dark noise at 0 degrees Celsius. If I go 6 degrees Celsius, then this is a factor, this is 2. So that tells me that the dark noise is twice as large at 6 degrees. So we say that the dark noise has a doubling temperature of every 6 degrees Celsius. So if I go from 0 to 24, that's 2 to the 4, or 16 times larger dark noise. If I go the other way, then it's smaller. So what I can do is compare the dark noise to the read noise and see when they start to be equal. If I have dark noise is equal to the read noise, or say I want to do 4-minute exposures, then I have to cool my sensor below, let's see, 12 degrees or something like that, in order for the dark noise to be equal to the read noise. If I want to bury the dark noise and say it's 1/10 the read noise, I have to take my sensor at 4 second sub-exposure length, and I have to cool it down to -8 Celsius or so. So this is a good exercise to go through just to make sure that you're cooling sufficiently to remove dark noise from your image, because if you have extra dark noise, it's just going to reduce your dynamic range. In the best case, you can fully eliminate dark noise by cooling to bury it as much as you can. Yeah, so in this case, this is a camera that has very low dark noise and very low read noise. In one point I want to make is that it's all camera specific. So if this is your mark that you want to go for, that the dark noise is 1/10 the read noise, and I want to go for 4-minute exposures, that says I need to cool to at least 8 below. It doesn't matter, you know, if I can cool to -20, well, that's fine. But really, I'm getting you know, limited returns on that extra cooling by doing that. And maybe I image in the summer and I can only cool to -8, -10. In the winter, this is no problem. I can easily do that. But in the summer, I may not be able to cool down to -20. And in this case, this camera works well for that. In the case of the 8300 Kodak sensor, if I were to do the same exercise, if the dark noise is equal to the read noise, I would have to cool to 6 below. For the same condition where I want to bury the dark noise to be 1/10 the read noise, I would have to cool to, I think, -30 or something like that. So the cooling requirements for this sensor are a lot higher than for the other sensor, just because of the way the dark noise and the read noise trade-off looks. That said, the cooling for this is a bit stronger because the CCD sensors, they don't have a readout at every pixel. So the CCD sensors don't often put out that extra heat into the chip as the CMOS does. But either way, this is a nice comparison to tell you if you're cooling enough. If you need to cool stronger to reduce that dark noise as much as you can. Questions on that stuff? Okay, and now we're going to shot noise. This is present in all of our signals. This is present in read noise, dark noise, our sky source noise. This is present in the sky background noise. And really, shot noise is what's called a Poisson noise. It is a noise of counting something. So it could be anything. In our case, it's photons per second, or equivalently electrons per second. It could be number of raindrops falling into your rain gauge per minute. It could be the number of blue cars passing an intersection per hour. But really, all this is it's saying, what does the noise look like? What is the distribution of counting something that happens every n minutes or n seconds or something like that? And this is the way it looks. If lambda here is the rate, so this would be like 1 raindrop per minute. I might get 0, I might get 1. If I go to 2, the probability of observing 2 when the rate is 1 is low. The probability of observing 3 is even lower, and so on. If I have a rate of 10, it's centered around 10, and this probability looks almost like a bell curve. And actually, when this goes large, it basically is a bell curve. But one interesting thing about this distribution that's a neat property is that the standard deviation, how wide this bell curve is directly related to this value of lambda. It turns out that the standard deviation is the square root of where that number is. So if we measure a signal, say we measure 100 electrons, that's our signal. And then our noise is the standard deviation value, which is the square root of 100. So we have a signal to noise of 100 divided by square root of 100, which is 10. So the signal to noise of 100 electrons being measured, in this case, would be 10. If I go to 10,000 electrons, the signal is 10,000. The noise is square root of 10,000, which is 100. And then the ratio of signal to noise would be 100 to 1. So as we increase this, this rate, as we collect more photons, as we stack more images, our signal to noise increases by the square root of the number of electrons or photons we collect in that stacking. And that's why we stack. The stacking reduces the noise because of this property that as you increase the total value of this, the bell curve shifts to the right, but it also tightens in a relative way to where the signal to noise always increases with the square root of that number. And we can take that and convert that into what our signal to noise would look like on a pixel level. So our signal of interest is the object signal, and the noise attributed from the shot noise of each of these components, the light pollution, the read noise, the dark current, the signal of our target, is all down here, and this is all the noise component. So the signal to noise of the pixel would be just this relation here. And the reason it's the square root is because of that Poisson process, where we're taking the standard deviation is actually the noise, which is the standard deviation, is the square root of that number. And then if we add in calibration, we have to add in the noise from those calibration frames as well, and they would add in this way. And you can measure a lot of these properties, the gain, read noise. We can calculate these. You could calculate them in PixInsight, which is done here. You just feed in a few flat frames, a few bias darks. Or if you want to get hands-on, you can actually do them yourself with a calculation, just adding the flats together, taking the mean over the variance in this way, and calculate the whole thing this way. Interestingly, in PixInsight, what they call dynamic range, I don't know if this is correct, where they say steps, sorry, I initially read that as stops. This is just the ratio of the full well capacity, which is this value, divided by the readout noise, which I think is this value in electrons. And the dynamic range, as we saw before, you would have to take logs in order to convert that into steps or decibels. But yeah, that's how you can compare different cameras with the dynamic range. Any questions on any of that?
Okay, so this is kind of blowing my mind with respect to shot noise. Didn't realize that there was shot noise in all the different noise components. Usually,
Yeah.
Usually they refer to shot noise as just associated with the randomness of how the signal is coming in.
Yeah.
But I guess I just don't see how the shot noise plays into the read noise and the dark noise.
Yeah, so when I say noise, I still say that it's just random fluctuations you can't remove out. So the shot noise is a counting noise, so it's counting by a rate.
Okay, so it's strictly a counting noise.
Yeah, so that would be the dark noise, because that's a rate, that's a number of electrons per second. Yeah, likewise with light pollution and signal.
Yeah.
Read noise in this case is kind of like shot noise, but it is shot noise which does not scale with time. It has a distribution, and I guess depending on which, let me think. And now that I think about it, okay, read noise may not be directly related to shot noise, because it doesn't have this. It's not guaranteed to have this type of distribution. Mm-hmm. In some cases, you'll have a long tail, especially, for example, if you do have amp glow, you'll have a distorted distribution like this, and that's fixed. That doesn't, that doesn't change with time or doesn't change with cooling or anything. But regardless, each of these bars has a base level. So say we have 50,000 electrons from our signal, but that edge here, pixel to pixel, changes, and that variation, pixel to pixel, is the inherent shot noise.
Right.
Likewise with light pollution, and likewise with dark noise.
Wow. Wow, that's interesting. I don't think I'm going to bring that up in my class tomorrow.
Yeah.
Because right now I'm only associating the shot noise with the fluctuation in the signal itself.
I mean, shot noise is usually taken as the signal, but everything here is being
Yeah.
measured.
Yeah.
It's only in our brains are we isolating signal from the rest of it. Just because in our brains it's isolated doesn't mean that each of these has different behaviors. They all have the same behavior. They all have the same randomness. Yeah.
Wow, that's quite the revelation, Gabe.
And then, so when you have the read noise, you say you cool the dark noise to oblivion, you have read noise that's left over. You can't remove that. So a lot of times people use this term sky limited exposure. How much time do you need to expose the sky to your chip, or expose your chip to the sky to where that photon flux becomes large enough that you can barely notice the read noise. In that case, your subframes will be more reflective of the sky and less of the instrument that you're using, of the camera you're using. So you're overwhelming whatever, say, pattern noise or maybe amp glow, if the amp glow is faint, you can expose to saturate that and or to overwhelm it so it doesn't become noticeable. And you can make that calculation. The way you would do that is you would say that the T is time here, E sky is the photon flux from the sky. So this would be, say, the light pollution or the light pollution plus signal. A lot of times people just say it's the light pollution because it's the strongest component in a lot of cases, depending on where you image. So it's saying that how much additional fraction would the read noise contribute to my total image? That would be, so read noise plus the sky is effectively the sky plus some small percentage. And this P is taken to be a couple percent, maybe like 2 to 5%. And so if you change this around to find T, you can calculate T by saying the read noise squared over this whole expression. So if you put in a very small value here, say 1%, so 1.01 squared minus 1, that's going to be something very small. So that tells you that your time has to be large. If I put in, say, 10%, then you don't have to expose for as long. If you want to accept, say, that your total noise is 10% from the read noise. A lot of times, I think I've seen a lot of times people use 5%. And in this case, it gives a decent value for time. So this is measured from the camera. This is, you choose this value, 5% is fine. And then E sky is the number of photons that you would get, the equivalent electrons from the photons you would get from the sky. And the way you do that, you can get that by taking just a test image, measuring its ADU value, subtracting the pedestal, which is really like subtracting the bias. So subtract the bias from this test image, divide by the total exposure time, multiply the gain, and that's the number of electrons per second in the sky. And you can use that here for this. There is a tool in PixInsight for this calculation that you can use as well. I'm sorry, I don't think I had a screenshot of that, but that's also there. Actually, yeah, calculate sky limited exposure. It's this one right here. Okay, so the point is this is really a big consideration when you're doing narrowband, because the sky flux in narrowband is very, very, very small. Narrowband is cutting out almost all wavelengths except the H alpha plus or minus a few nanometers in some cases. And because that sky flux is small, this time needs to be a lot larger in order to saturate the read noise, to overwhelm the read noise. And that's why for narrowband, people image for 15 minutes, half hour, up to an hour in some cases I've seen. For RGB or luminance, it's not that much of an issue unless you're imaging sort of on the less than 30-second time scale or something like that. It just depends on the camera. But for most images that I take, 5 minutes, 3 minutes always does the job of saturating the read noise. So there is this trade-off. We've talked about a lot of different effects for signal to noise. Read noise is a big one. Dark current's another one, but we can treat that with temperature, thermoelectric cooling. We have other things though, the total exposure length. So say I want to take 4 hours, or say I want to take an hour of M31. And I know my read noise on my camera. I know my sky limited exposure. And I want to try and balance between overwhelming the read noise and the number of sub-exposures I want. So this sub-exposure length is sort of a delicate thing where we have to decide, do we want to, in that 1 hour, we want to take 61-minute images, or maybe 2 30-minute images, or one 1 hour long image. All these considerations go into play. So the total exposure length, the read noise, obviously, temperature changes. Maybe the temperature's changing over the night pretty quickly. And if that temperature changes fast over the time of your sub-exposure, you make it bad focus. Cosmic ray hits. When you combine all your sub-exposures, you do rejection, pixel rejection. So for cosmic ray hits, if you only have, say, 2 or 3 sub-exposures, those cosmic ray hits will be more obvious in your final combined image, because they won't get rejected as easily. Also, by extension, airplanes and satellites that go across your frame will be there. And then on the flip side, if you have a very short sub-exposures, you have you would have hard disk drive space issues in some cases. For example, the ASI 6200, each sub-exposure is over 120 megabytes in size. And so that'll quickly run into an issue with hard disk space. So on this, let me get zoom out of the way here. On this plot on the right, what I'm showing is a comparison of signal to noise ratio. On the top is the absolute signal to noise ratio. This is for a fixed 1 hour. I did this earlier today, just sort of sketch out these concepts. I did a fixed 1 hour total exposure. And then I calculated with the read noise of 8 electrons and a sky flux of 100 electrons per second. As you change the sub-exposure length, what the signal to noise ratio looks like. And what this tells us is that after a certain point, the signal to noise ratio saturates. If you have a lot of small, remember, we're subdividing each of an hour into each of these segments. So if I have 1 hour at 60 seconds, then I have 60 sub-exposures. Down here, I have maybe 200-300 sub-exposures of 20 seconds or so. And in that case, the signal to noise is a lot lower because you're not overwhelming the read noise. You're not saturating the read noise with the sky background, the sky flux. So at some point, there's this crossover where you do have this leveling off in signal to noise, and maybe it's okay to choose 100 seconds or 150 seconds instead of something that's 10 minutes or something. And that's where this trade-off of cosmic ray hits, airplanes, satellites comes into play. Because if I go crazy and say that I want to maximize my SNR no matter what, no matter how shallow this curve is, I want to take 10-minute exposures in 1 hour. So I have six subframes. When I combine them to do rejection, I'll have a harder time with satellites, airplanes, and cosmic ray hits because I only have 6 frames to do the rejection on. But if I do it down here at 100 seconds, I'll have more frames in order to do that rejection on. And so this is the total SNR in this view, and in this view, it's the SNR divided by the maximum SNR. So I get about 95% of the way there if I take a 2-minute exposure. So I have 30 30 subs. With that, there's a good deal that good chance that I'll reject all the cosmic rays, airplanes, and satellites that come across my image in that case, but still achieving 95% of the SNR. Okay, yeah. And then, so these are the same plots, but just showing how different read noise comes into play. So the red and black are the same sky flux. The red here is twice the read noise. And again, this is the total SNR, and this is the SNR divided by the maximum. So you can see that at 8 electrons, I have to image for almost twice as long in order to get the same SNR saturation level, to get as high of a SNR, 95% of the maximum SNR as I could. If I increase the sky flux, the total SNR goes down. So that's what this plot is showing, that is that they saturate at a different level. But in terms of the maximum, the conclusions don't really change here, that you want a low read noise. It gives you about twice as long a sub exposure if you have twice as much read noise, more or less. So this is just saying that brighter skies means lower SNR, which totally makes sense. And more read noise means longer sub exposures for the same SNR saturation. And then these are the same types of things with quantum efficiency. Quantum efficiency at 50 and 80% for the black and red. So it's just scaling that down by that ratio. And likewise for the brighter sky, it's scaling that down by that ratio as well. And then our crossover over 95% changes. So at 80% quantum efficiency, bright sky, our optimal sub-exposure length is shorter than at 80% dark sky. And it's shorter because that bright sky saturates the read noise faster. So we can just move on to the next sub and accumulate our subs that way. And we can still get to the same relative saturation of SNR. That said, we're still getting a lower SNR in the end because we have a brighter sky. So, and then, so a couple comparisons with all this in mind. A couple comparisons I made 6 months or so ago when I got a new camera. I went from a QHY 16200A, which has, let's see, a quantum efficiency of, oh, is it on here? I thought it was on here. Quantum efficiency, I think, of around 60%, and a read noise of 8 electrons. And I went to a ASI 6200M. The quantum efficiency is around 91%, so quite a bit larger, and then the read noise of 3.5 electrons. And this is a comparison of an area in Cygnus. I hope this plays okay. Here we go. So this is a comparison of the two subs, identical exposure lengths. So this is the ASI 6200 is the higher contrast one, and the QHY is the lower contrast one. And you can see that there's quite a big difference between the two, and that's largely because of the read noise and the quantum efficiency. We're getting more signal quantum efficiency, and we're having a lower noise floor because of the better read noise of the ASI. And then let's see, and then this is the gain plot of the ASI. So when you go to ASI's site, for a lot of their cameras, they show this type of thing. They show the full well depth at different gain units, the gain in electrons per ADU. So as you increase the gain, this value smoothly goes down. Excuse me. And then the dynamic range, which we've gone through that calculation with the ratio of this value and this value, take the log and so on. The dynamic range in this case, I'm sorry, full well divided by read noise. That's the dynamic range, not the gain. The dynamic range in this case, it starts off around 14 stops, which is really, really great. Decreases as we decrease the full well, but the gain stays relatively flat. And then they have the high conversion gain cutoff. So they switch from a low conversion gain to a high conversion gain. And I think internally the electronics changes fundamentally that makes this shift. And so the read noise drops by over a factor of 2 in that time. I'm sorry. It drops by over a factor of 2, and we recover almost the entire amount of dynamic range by setting the gain to be this value. It's not higher than this. This is still the highest dynamic range, but this is still very close to that, and it's a higher gain. So we're pulling in, you know, we're getting a brighter signal in the end. And this is a comparison of the Veil Nebula between the high gain and low gain. Exact same telescope, same night, same exposure settings, and it shows the brightness comparison between the two.
Hey, Gabe, that spot on my camera, the ASI 294, is where unity gain is considered on in the camera as well.
So this point where it abruptly jumps up, that's considered unity gain on that camera.
Yeah, my camera, it's about 120, and on those charts, 120 is where you see that significant drop.
Okay, cool. Yeah, I'm not sure exactly where my unity gain is. I just know that in my settings they say this is the highest dynamic range, and then this is the other setting that might be also unity gain. Offline I can take a look at it and see if that matches what you see. Good. Right, thanks. All right. So that's all I had for electronics. We have a lot of more topics for down the road. Different cameras and settings. We talked a little bit about that, but I'm sure there are other cameras, not just CCD, but DSLR and other options out there that we can discuss. Calibration frames, acquisition software. I know we all use different acquisition software, so it's good to get a flavor of what's out there. I think if we all kind of maybe chip in on that, do kind of a potpourri type of presentation where we all give maybe a 5-10 minute spiel on our software, that would be kind of neat to do. Target planning and sequencing, data management, weather, observatory topics, and also processing topics. So this was the start of this whole group was processing in PixInsight. We moved to this, but we can also go back to the PixInsight or Photoshop. And yeah, so next time is December 9. I know that's around Christmas, so you know it's the holiday season is upon us there, and we might all be busy. So it's an open date, whether we want to meet or not. It's, you know, I have no druthers on that. We could do right now. Nobody's committed to it, so we could either skip it or we could do PixInsight, Photoshop. Just have an open forum where we all kind of just chat about what we're working on or questions, or any of these topics as well. So that's it.
I was going to do a mosaic demonstration.
Okay.
I could do that on the 9th. It's short. It's only about 10 minutes.
Yeah, that'd be great. Yeah.
In fact, I'm working on a mosaic as we speak.
I think I owe the group a demo of Nina as well, but I'm not going to be able to do it on the 9th of December because we have a big go live in Illinois on the 6th of December, and I can't commit to the 9th. I don't know if I'm going to be available, but I could do it in January.
So we can, yeah, we'll exchange emails and plan for January to maybe do the acquisition software, and we can have Nina, SGP. I can do Voyager because that's the one that I'm using. But
I'm not the only one using SkyX, right?
oh yeah, we can do SkyX as well.
God, you forgot the most important one. I think some of these sites at the club use SkyX, right, Thomas?
I think G-scope is SkyX, isn't it?
Both G and F scope.
GNF?
Yes.
Yeah. Okay. So that'll be an important one to, I can do SkyX.
Cool.
Okay. Any other questions? Or...
Whew. I got to go put my head in ice.
I want to thank you, Gabe. This is a nice technical discussion.
Yeah.
We all learned something.
Thank you, Mike. Appreciate
Yeah,
that.
thanks, Gabe. I appreciate you doing this. You'd think you were a physicist or something.
Yeah, really.
Former life.
All right. Thank you.
Thanks, guys.
Yep, thank you.